For part 2 of this lecture 9, we will consider the following. We will look at finite state machines, introduce what finite state machines are. We will then turn our attention to designing synchronous counters. And note that this part of the lecture, the first part would be from section 9.1 of the book, and the second part would be from section 9.5 of the book. Now, the definition of a finite state machine is that it's a sequential circuit, which means it's got memory, with which traverses a number of states, a limited or finite number of states, hence the name finite, and these states occur in a prescribed order. So there's a certain order in which through which the states, the circuit goes through the states. So a finite state machine is a sequential circuit that goes through finite states in a prescribed order. And the example of that is simply the counter, which we've looked at in the previous part, either being in a synchronous or an asynchronous counter. That would be an example of a finite state machine. Now, there are two types of finite state machines, and they are normally called either the Mealy machine or the Moore machine. And these types differ in their structure. So, first of all, the Moore machine. For the Moore machine, the output of the Moore machine depends only on the internal state of the machine. So the internal state, which is stored in memory, is the one which determines the output of the Moore machine. Now, the Mealy machine, on the other hand, the output of the Mealy machine is determined by both the current state as well as the input. So as much as both of these finite state machines have the same structure. So a finite state machine would have a structure whereby it has memory in combination with combinational logic. Memory with combinational logic. Memory, combinational logic. But the difference is that the Mealy machine, for the Mealy machine, the output is determined by both the internal state plus the input, whereas for the Moore machine, the output is simply determined by the internal state. So an example of a Moore machine would be a counter. Remember, a Moore machine is a machine whereby the output is merely determined by the present state. Now, imagine a counter which is used to control a bottling plant, such as this, for bottling pills into a bottle. So let's say you have a bottling plant which bottles 25 pills per bottle, and the counter works in a sense. It will use a Moore machine, because in this case the Moore machine, the internal state is the only one that will be able to determine what the output is. So we take an example of a counter which counts a modulus 26 counter, which counts from 0 to 11001, and the way it works is according to this finite state, what's called the state diagram. So in the state diagram, we have the states. The circles here are the states, they represent the states, and the arrows here represent the transition from one state to the next. So what would happen in this case is that at state 0, when the counter is counting 0, the bottle will not be in place. The next bottle comes into below the dispenser of the pills, and as it comes to that, the controller, which is the counter in this case, would then enter state 1. It will enter state 1 by releasing the first pill, and then it enters the state 2 by releasing the second pill, 3 the third pill, and so on and so forth, up to it releases the 25th pill. On the 25th pill, then it stops and it transitions back to state number 0, whereby it requires that the next bottle should be in place. If the next bottle is not in place, it will remain at this binary state 0 up until the next bottle is ready, so that it can bottle it by counting in all of these 25 pills. So the structure of such a controller would be in this format, whereby you have the flip-flops making up the counter, and you have a logic a circuit which decodes the logic so that you are able to understand if 25 or the maximum count of 25 pills has been reached. And in this flip-flop, obviously transitions from one state to the next using a set of combinational logic. And so this could be your example, a typical example of a synchronous counter, which we have seen previously. An example of a melee machine would be, say for example, you have a similar example as the previous one, but this time around you have a version whereby your bottling plant is able to bottle 3 different types of bottles. The bottle that contains 25 pills, 50 pills, and 100 pills. And you are able to select which one you want to bottle. So in this case, you might have at least a modulus 100 counter, a counter that can count further than 100 steps. And then you can have an input to that which selects the maximum number of count that you want. So if there is a bottle with 25 that takes 25 pills in capacity, would select that. The system should give you you should be bottling for 25 pills, and the way it would work is that the different states here as it transitions. So whenever it's waiting for a bottle, let's say it's waiting for a bottle, depending on the input that it receives, it will either transition from one state to another. So if it receives, say for example, input which says now it's bottling 25 pills, then it will go into this state, and then it will count from 1 all the way to 25, and then it transitions back, or depending on the input, if it's supposed to put in 50 pills, then it might be that it goes on up until it counts to 50, and then it transitions back. So depending on that, or sometimes, so it bottles 50, sometimes it can bottle even some more, 50, 51, 52, and so on up to 100, and then it transitions back. So the output here will depend on both the inputs, which is what type of bottle that is, what type of, what size of bottle, or how many tablets or pills it's bottling, which is the input, and it also depends on the present state, at what state is it in. So both of these two inputs will determine the output. So in this case, this will be an example of a melee machine. Now we have to know that in fact we can design these finite state machines, or simply placed, these synchronous counters. We can design them to transition through any transition of predefined states, any predefined number or pattern of states. We can be able to design that. Say for example, we want a counter which goes through the following. It goes through 5, it goes through 7, it goes through 1, it goes through 4, 5, and so on and so forth. So we can have a counter which transitions through 5, 7, 1, 4, and back, and so on and so forth. So we could have such a finite state machine or synchronous counter that we can design, and we can design it to transition through any pattern of states that we want. We could have one that goes 1, 2, 3, 4, 0, and so on and so forth. Could have something like this, or we could have something like that. Whatever states and whatever pattern and whatever range at which we want it to go, we can have such counters. And this can be achieved by a simple procedure with just 5 steps. And we'll now look at those 2 steps, those 5 steps, I mean. Now, the 5 steps that we are going to go through is, in order for you to design this final state machine that you would want with any pattern of states which you desire, you would need, first of all, in step number 1, to develop a state diagram for a given sequence. Step number 2, you need to develop the next state table. Step number 3, you create flip-flop transition table. Step number 4, you use the K-maps or the kernel maps for combinatorial logic. And then finally, you would implement your counter, the logic of your the combinatorial logic of your counter that you have derived from step number 4. And this procedure, mind you, is applicable whether you're using for your memory JK flip-flops or D flip-flops. In fact, we will just take an example, a simple example. We'll go through the design process using D flip-flops and then go through the same design process using JK flip-flops. Now, let's say, for example, we have a design task to use D flip-flops to design a synchronous counter that goes through the following sequence. So our counter goes through state number 1, state number 2, number 5, number 7, and back 1 to 1 again. So it goes to 1, 2, 2 to 5, 5 to 7, 7 to 1, and so on and so forth. So it goes through that sequence of steps. We can show, in fact, that we can use these 5 key steps to design this counter without any problem. Let's look at that. So the first task of this design problem is to tackle step number 1. And step number 1 says we need to design a state diagram. So state diagram, we simply write the state transition into a state diagram using binary code. Binary code. The reason why we want to use binary code is to try and understand the encoding of these numbers or the states in binary. And we will see that, in fact, for all of these these 4 states or 4 digits that we need to have here, in binary we need a maximum of 3 bits to represent them. Because we have a maximum of 3 bits, we can therefore tell that whatever we do, we are going to need 3 flip-flops in our design. So this is what first the state diagram tells us. So we encode your states into binary code. We will clearly sketch it to see what transitions it needs to go through, and you write them in binary code. Afterwards, then you will know that what's the number of flip-flops or memory elements that you need. So the next step is to go through step number 2, where we derive the next state table. So we have already drawn our state transition diagram. Now the current step is for us to draw the state table. So the way you draw the state table is simply as shown here. You simply draw up in tabular form the transition. So you draw up the first few columns to represent your present state, in which case you will need 3 flip-flops, Q0, Q1, and Q2, in that order, so that you know which one holds the most significant bit and which one holds the least significant bit. And then this one will hold the most significant bit. And you then write down the states in which you need to go through. So the first state, you need to go 1, you need to go 2, you need to go 5, 7, and then you are back at 1. So you write those unique states that you need to go through. And in the next column now, you're going to draw up the columns of the next state. So what you are saying here is simply when your states are 0, 0, 1, when you're at 1, what will be your next state? So when you're at 1, according to this, your next state is going to be, your next state is going to be 2. So when you're at 1, your next state is going to be 2. So you write the 2 here. And then when you are at 2, your next state is going to be 5. But when you are at 5, your next state is going to be 7. And then when you are at 7, you are going to have your next state going back to 1. So now you're done with your state transition. So ultimately then you will have a table similar to this one, right? Now you go to the next step. The next step here is to now fill in the flip-flop transition table. For the flip-flop transition table, it depends on the flip-flop that you're using. In this case, we are going to be using the D flip-flop. So what we need to do here is to try and understand the values, the value of the inputs at the flip-flop that will force it to transition from the state, from the current state to the next state that we desire. So in this case, remember we have determined that if this is the present state, then the matching next state will be that. Now what we do from here is to then determine what should be the inputs based on the present state so that we can get the next state as this. And we can see that from the flip-flop transition table of a D flip-flop in this case, because we're going to be using the D flip-flop, we will see that in fact, if we want our flip-flop transition from 0 to 0, the input has to be 0. If we want it to transition from 0 to 1, the input has to be 1. In fact, we can see that the input of the D flip-flop simply has to be equal to the transition that we want it to be. So if we want it to transition to 0, the input has to be 0. If we want it to transition to 1, the input has to be 1. So in this case here, let's consider here the most significant D flip-flop number 2. So D flip-flop number 2 will have a Q output of 2, and we want it to come it will have a Q output of 0. We want it to come to a Q output of 0 in the next state. What do we do? What should be the input? The input should be 0. Because in fact for a D flip-flop it's easy. The next state is simply equal to the input. So in this case, because we want it to be 1, it will be 1. We want it to be 1, it will be 1. And it will be 0. Here we are looking at, for D1, we are looking at Q1. We want it to be 1. We want it to be 0, 1, 0. We want it to be 0. We want it to be 1. We want it to be 1, 1. So in this case, now we have finished the flip-flop transition table, which determines the inputs. The next step now is to go through the K-map, the Kano maps. So in the Kano maps, we are simply going to be plotting these outputs. D2, the output, the inputs D1, and the inputs D0. And we are going to see what type of combinational logic takes this input of the present state and give us this inputs D1, D2, D0, so that we can have the transition that we wish to have. Now in the process of this determination, what we need is to create a K-map for each and every one of the flip-flops. So we'll create a D2 K-map, we'll create a D1 K-map, we'll also create a D0 K-map. And in this K-map, we are going to plot the inputs, which are the red present states, how they determine our outputs, which is this D's. So let's take, for example, now for D2. For D2, we see that there is a 0 at an input 0, 0, 0, 0, 1. At input 0, 0, 1, there is a 0. Got a 0 there. So this 0 is from here. And then we see that there is a 1 at 0, 1, 0. 0, 1, 0 is a 1. We see that there is also a 1 at 1, 0, 1. At 1, 0, 1, there is also a 1. We see that also there is an input here. There is an input 0 at 1, 1, 1. At 1, 1, 1, we have a 0. So this will therefore map into that. So because now these are the predetermined values that we need, the rest we don't care. So we'll just put them as don't care states here. Right? And then we go to the D1 map. In this case, we are looking at the first one. At 0, 0, 1, at 0, 0, 1 we have a 1. At 0, 0, 1 we have a 1. At 0, 1, 0 we have a 0. At 0, 1, 0 we have a 0. And then at 1, 0, 1 we have a 1. At 1, 0, 1 we have a 1. And then at 1, 1, 1 we have a 0. 1 we have a 0 here. The rest we don't care. We do a similar map here for this particular column, and we see that we have a 0, 0, 0, 1, 0, and then 0, 1, 0, 1, which is that, and then this one is 1, 0, 1, we have a 1, and then this is 1, 1, 1, that one, and the rest we don't care, we don't care, we don't care. Right? So that then completes the first part of the K-map step. Because remember, the K-map has to be reduced so that we can get the combinational circuit. So finishing off the K-map, we need then to create the combinational logic circuits that are going to be accompanying our D2 map, D1 map, as well as the D0 map. Now we have filled in our K-maps. We now need to reduce them to their simplest circuits. And we can see that in the first K-map, we can make the following groups. Here's the first group, the red group, and then we can also have the second group, which encompasses this one. That could be our second group. And we can therefore see that this means our D2 is equal to, we will see that our D2 is equal to, if we look at this red group here, we see our D2, as we move this way, we see that Q naught does not change. We see that the Q0 bar does not change. Q0 bar does not change, and this is accompanied by a 1 at Q2. So it's Q2 and Q0 bar. And if we look at this group, we see that Q2 changes because you can move up and down the group. You can move up and down the group, so Q2 changes. So Q2 is eliminated, but as we move from this to there, from here to here, we see that Q0 remains 0. So we have Q0, which is Q0 bar. So in this case, we have the Q0 bar. So this group gives us that. So now it means at the input D2, we should have these combinational circuits. Now we have the second one, which is the D1. So D1, the way we look at it is we do it in the sum of products, obviously, and the biggest cycle that we can draw here is this. The biggest group is the group of 4s. Remember, you can always go back and revise your K-maps. There's a video that I've just put up. So you have your biggest group, and you can see that as you go from here to here across this group, as you go across this group, you see that Q1 remains 0. It remains low. Q1 remains low, so you have Q1 bar. As you move up and down, you see that Q2 changes. So Q2 is eliminated. Even if as you go this way, you see Q0 changes. So therefore, it means this group gives us just Q1 bar. And the final logic here, as we try and create the biggest group, we will see we can encounter that. Group of 4. Remember, you can't do a group of 6 here. So we have to be a group of powers of 2, and then you can make a bigger one here as well. Then you'll have encompassed all the ones. Remember, we care only about the ones if you are doing the sum of products. Now, what will happen is that this group, you see that as you move through this group this way, Q1 and Q2 and Q0 always change. Between these two, you see Q0 changes from 0 to 1, so Q0 is eliminated. Between these, you see Q1 changes from 0 to 1, so Q1 is eliminated. But what you do remain with is Q2, which is high. Now, if you look at this particular group, for that particular group, as you move up, down, Q2 changes from 0 to 1, so Q2 is eliminated. But you see that as you move this way, across this way, you see that Q0 changes from 0 to 1, but Q1 remains. So Q1 remains. So in this case, you'll have Q1 remaining as 1. Therefore, your products that you need to sum, it's going to be Q2 plus Q1. So now you have just created your 3 combinational logic inputs to the D flip-flops. The next step now is about implementing the counter, the logic. So in this case, you have your 3 inputs. You have that input to D0, that input to D1, and that input to D2. Now remember, this is a synchronous counter, so which means the first thing is you draw your flip-flops, the 3 of the flip-flops that you said you're going to need 3, and out of those 3, you tie them all to the clock because this is a synchronous counter that we are designing. And now what you are left with is to create the inputs. So at the input here of D0, we have an OR gate. So we have an OR gate which has the inputs as Q2 and Q1. So let's draw that. We have an OR gate here. And then this OR gate, we are going to have our inputs as Q2 and Q1. So we'll take this Q1, so it doesn't come here. Go in there, and then we'll take this Q2, right? So we are done with this now. Now the input of D1, is Q1 bar. So because Q1 bar it's here, immediately we take that Q1 bar. We are done. We don't even need a gate there. That's Q1 bar. And then at the input of D2, it's 2 logic gate. We have a small AND gate which fits in a bigger OR gate. So first of all, we need to have a bigger OR gate fed by a small AND gate. Right. Now the OR gate fits. So this input to the AND gate, it's fed by Q0 bar and something. So it's Q0 bar. So let me take that Q0 bar. I'll draw that this way. And the input of the AND gate. The AND gate is made up of Q2 and Q1 bar. So it's made up of Q1 bar and Q2. So it means then I can take that. Okay, I can take that. Now I've just implemented my counter. This then becomes the right solution for my counter or the final state machine that goes through the sequences. So if you check the solution in your book, this should be the solution. So you have your equation here, you have an OR gate at the entrance of Q0 at DU0, and then you have your AND and OR gate at D2, and you have your Q1 bar at D1. So this finite state machine will transition from 1 to 2 to 5 to 7 and back and forth. So we have just created a design here of a synchronous counter which goes through this predetermined sequence, which is not very normal. So it therefore means we can use the same procedure to do any arbitrary combination of sequences or predefined sequence, pattern of predefined sequence. So let's take the same task of developing a synchronous counter going through the states 1, 2, 5, 7, 1 again, and so on and so forth, using JK flip-flops. So the first step, as we're using in D flip-flops, becomes drawing up the state diagram, and the step becomes identical in the sense that we write binary code for all of these four states. The 1 becomes 1, and then we have 2, which is 1, 0. 5, it's 1, 0, 1. And because you see 5 requires 3 bits, we'll encode the rest of this with 3 bits, because all of these four states can be represented with 3 bits. So we will require them to represent all of the states in 3 bits, and therefore similarly we're just going to require 3 JK flip-flops. Now our next task is to draw the next state table, and in that task then the table remains the same, because remember the next state table simply says it's simply a different version of the state diagram itself. It shows how the present state changes into the next state, and all of this we do in preparation to drawing up the flip-flop transition table. Remember, in this case, I think what we need to keep in mind is that there is a different way in which the JK flip-flop operates as opposed to the D flip-flop. So for the JK flip-flop, a transition from 0 to 0, when you want to remain in the reset state, the input J has to be 0, but the K doesn't really matter. And when you want to transition from 0 to 1, the input J is 1, this is the set state. And when you want to set it, the input J has to be 1, the K doesn't matter. So in fact, you see that when you are moving from a state of 0 to any other state, all you care about is the J, the reset, the set input. So when you're moving from 0, all you care about is the J, and the K doesn't really matter. And if you are moving from 0 to 0, the J is 0. If you're moving from 0 to 1, the J is 1. On the other hand, if you are moving from a state of 1 to the next state, all you care about is the K in that case, and the J doesn't matter. So the next state here follows the K input if you're moving from 1. So if you're moving from 0 to 1, you are resetting, the K has to be 1. If you're moving from 1, you are remaining at 1, you're not changing anything. It means that for your K is 0, because you're not resetting. So now we move to the next step of drawing up. So at this point in time, it comes to step number 3, and the objective of step number 3 is to develop the inputs to the JK flip-flops. And we have now determined the next state table. we know what the present state, next state pairs that correspond to each other for each of the 4 states that we wish to transition to. So in this case, we see, for instance, here in the first example, we see that we need to transition from 0 to 0. So in our case, where we need to transition from 0 to 0, this corresponds to this very first row of the transition table. So in that case, what we see is that our inputs to the JK flip-flops is 0, don't care. And then the next state we need to transition from 0 to 1. Because we are transitioning from 0, we don't care about the K, but we know that the J has to be 1. We are transitioning in this case from 1 to 1. Because we are transitioning from 1, we don't care about the J, but we know that the K becomes 1. In the next state, we are transitioning from 1 to 0, we don't care about the J. This has to be 0. And so we can fill in this table. We can complete this table now, even for the flip-flop number 1, Q1, from 0 to 1. From 0 to 1, we don't care. This is set. From 1 to 0, we don't care about that. And this is a reset that we have. And then you're transitioning from 0 to 1. From 0 to 1, we don't care about that. And this becomes 1. And then you're transitioning from 1 to 0. From 1 to 0 to 0, we don't. From 1 to 0, we don't care about that. But this becomes a 1. In fact, here I've made a mistake. In this ones. This has to be 0. This has to be 1. Because remember, if you are transitioning from a 1 to a 1, from a 1 to a 1, this is like saying you transition from a 1 to a 1. So your input has to be don't care 0. Just don't care 0. And so we can complete this. In this case, you're transitioning from a 1 to a 0. If you transition from a 1 to a 0, you don't care about that. This becomes a 1. If you're transitioning from a 0, you don't care about that one. Don't care about that one. You're transitioning from a 0 to a 1, but you know that you have a 1 here. Transition from a 1, you don't care about that. And then you have here a 0. Transition from a 1, don't care about that. We have here a 0. So now that you have completed your input to the flip-flops, the next step is to use the K-map. So we have now completed our flip-flop transition table, which is that. We now need to complete the K-map for each and every single input. In this case, we have 2 inputs for each flip-flop. So we have J2, K2, J1, J2, K2, J1, K1, J0, K0. So we have 6 inputs, which means we need to have 6 of these K-maps. In this case, I've just shown only 4 of them for illustration purposes. So for J2, we know that J2, in the first row, we see that we have at 001, we have 0. This is the one. At 010, we have. At 010, we have 1. And then at the next step, which is 10, 1, we have don't care. And then okay, so we have don't care here, and likely of course at 111 we also have don't care. And then for K2 we see that 001 we have a don't care, and then 010 we have a don't care as well. This is the column we are talking about here. And then we have the next one becomes a 0 and a 1. And then when we look at J1, which is that, we see that we have a 1, we have next they don't care, we have the next one as a 1 and they don't care. And we look at the K1, we have K1 we have a don't care, we have then a 1, we have a don't care, and another one. In fact, we see that since our transition table only has 4 entries into the K-map, it means the rest would then automatically become don't care as well. So the rest we don't really care. Because our transition don't include that. And here we look at the map now for the last two, which is that and that. For J0, we see that J0 we have in this case don't care. Oh, let me change my pen. For J0 here we have a don't care, we have a 1, we have a don't care, and another don't care. For K0 we have start with a 1, we have don't care, a 0, and another 0. It means then that the rest we automatically don't care because you don't appear in the transition table. So we have, now that we have our transition tables, sorry, K-map completed, we now move on to creating the input equations that will give us the combinational circuit. Now the first one that we need to look at is the map for J2. So in the map for J2 we can reduce this standard sum of products by grouping the ones, and we can group this one by making the largest possible group involving a 1, which has 4 items. And we can see in this group that as you move up down, Q2 changes, so Q2 will not be part of the sum of products. And then as you move across, you see that only Q1 remains high. This means therefore that the J2 will remain with Q1. So our equation then for J2, the input will be simply Q1. And then we look at the next map, which is K2. In the next map, K2, we can make this group as the largest group. And this we see that is identical to J2, and K2 as well will become simply equal to Q1. And then in the next map that we consider is J1, and we see that in fact here with J1 we can make the biggest group, which involves each and every entry here in the cell. And in this case, when we have this type of situation, It therefore means that your input is simply equal to 1, your logical high. So your input will always be high. And therefore our J1, the input becomes 1. And similarly with K1, we see that we can make this large group of 8 as the largest group because we have all of these nice and convenient don't cares. So it means now K1 is also equal to 1. We look at J0. With J0, we see we can also similarly do a very large group, which means J0 will simply be equal to 1. With K0, on the other hand, we see that because there are zeros here, the largest group that we can make is that. And with that group, we see that both Q1 and Q0 changes. They change in this group, so they are eliminated, but we are left with Q2, which is 0, which means K2 is just Q2 low. And so K0 simply becomes Q2 bar. Now that we've got all of these inputs, we are now ready to implement the logic of the counter. So at this stage, we have implemented the K-map, made a reduced equations for the inputs J2, J1, J0, K2, K1, and K0. So we are ready now to draw up the inputs of the flip-flop, and we can start with the least significant flip-flop here, flip-flop 0. And we see that if we start with flip-flop 0, our input here to J0, it's going to be 1. So we type this to VCC. That becomes our input for J0. And then the input K2 becomes Q2 bar. Q2 bar, we can simply take that. That becomes our input here. And then we move on to the flip-flop for J1. For J1, we see that it's also typed to VCC. And then K1 is also typed to VCC, so we take that, we type there. And then we move to J2. J2 is typed to Q. It's typed to Q1. So Q1, J2. And then K2 is also typed to Q1. So that completes our logic. In fact, amazingly, for this logic, we don't even need gates. And it can be implemented simply as that. And so if you sketch it nicely, then it should give you something of this sort. So we can see that this is a implementation of this particular synchronous counter. We can implement it using JK flip-flops in this very manner. So for revision, go and practice problems in sections 9.1 and 9.5, the design of a synchronous counter, in order for you to cement these concepts.